Today, I'm synthesizing dehydrozingerone, starting from vanillin and acetone through a base-catalyzed aldol condensation. In the paper I'm following, an ionic liquid was used to help the reaction proceed efficiently. In my case, I used a different ionic liquid in the hope of getting a comparable yield. I begin with a star bar in a 3-neck flask, then add 4 ml of 2.5 molar sodium hydroxide in water, followed by 200 microliters of the ionic liquid, and then 3.5 ml of acetone. I set the oil bath to 60 degrees Celsius and allow the mixture to come to temperature before adding the vanillin. To help it go in smoothly, I first dissolve the vanillin in a minimum amount of acetone, then add it dropwise with a pasture pipette so the reaction stays controlled. Now for the mechanism. Under these strongly basic conditions, hydroxide deprotonates acetone to form the enolate. That enolate then attacks the aldehyde carbonyl of vanillin, given the beta hydroxyketone intermediate. From there, base protonated dehydration removes water and forms the conjugated enone, dehydrozingerone. The driving force is the formation of the extended conjugation between the aromatic ring and the alpha-beta unsaturated ketone, which makes the product more stable. The ionic environment is important because it can change the reaction environment in a way that promotes the condensation. In the paper, the ionic liquid medium helps support the aldol process, likely by improving the phase behavior and influencing the microenvironment around the reacting species. I didn't have the same ionic liquid used in the paper, so I used this one as a sub and hoped it would provide at least some of the same beneficial medium effects, even though the outcome may not match the optimized literature system exactly. After the reaction, I checked the crude material by HSQC. The spectrum was useful for confirming that the product was in the right chemical family. I looked for the expected aromatic correlations from the vanillin-derived ring, along with the alkene and methoxy-associated signals, consistent with dehydrozingerone. That gave me confidence that the condensation had occurred, even though the sample was still crude. From the crude isolate, I obtained a 39% yield. That's lower than ideal, but still enough to show product formation and move on to purification. Overall, this synthesis shows how vanillin can be converted into dehydrozingerone through a classic aldol condensation and how changing the ionic liquid can influence the practical outcome, even though my substitute ionic liquid did not give an optimized result. The reaction still worked. Thank you so much for watching.